I'm Saritha Kumari, Assistant Professor, Institute of Aeronautical Engineering College, EEE Department, Dundigal, Hyderabad, under the course Performance of Transmission Lines and Cables. Today the topic is Numerical Problems on Corona Phenomena. This topic mapped to course outcome 4. So problem, a 3-phase 220 kV 50 Hz transmission line consisting of 1.5 cm radius conductor spaced 2 meters apart in equilateral triangular formation, given basically 3-phase line. Okay, 3-phase line. The conductor's radius is given 1.5 centimeter and distance between the conductors is 2 meters. Here they have given temperature. If the temperature is 40 degrees Celsius and the atmospheric pressure is 76 centimeter. Given temperature 40 degrees Celsius and specific values, but atmospheric pressure 76 centimeter. Then calculate the corona loss per kilometer of the line. Take m0 is equal to 0.85. So clearly they ask corona loss. That is a problem, and they have given the required data. So here see that how to calculate the corona loss. So basically, of course, these are the answers finally we need to get. So the corona loss is the this much. This is the answer. So now see that, and before that, to calculate that corona loss, we need to know the critical disruptive voltage also. So that value is mentioned here. So that is our value also given 125.9 kilovolts per phase. So first calculating critical disruptive voltage. Because in the corona loss, so the corona loss, that is nothing but corona loss is also nothing but power loss. So the equation for it is already we have seen in the previous lecture, 242.2 into F plus 25 by delta into square root of R by D V minus Vc whole square into 10 power minus 5 kilowatt per kilometer per phase. So this is the standard corona loss power equation. To calculate. So here see that. So in this expression, so this is the expression for given in kilowatt per kilometer per phase corona loss. Per kilometer per phase. This is now here in this expression. So what is this? Vc is the critical disruptive voltage. Standard notation, we already know that. So first we calculating that critical disruptive voltage, and also then the remaining parameters. Look at the remaining parameters. V is nothing but system operating voltage. System operating voltage, that is given 220 kV. I think, right? 220 kV only, right? So next, what else we have? So 220 kV is the line voltage. We have to take the per phase voltage 220 by root 3. This one we need to substitute 220 by root 3. Next, what about this square root of R by D? So square root of R by D, R is the radius, smaller, D is the distance spacing between the conductors. So it is given radius is 1.5 centimeter and meters 2 meters apart. So radius given in centimeters, of course we need to substitute, both are in centimeters. So as I explained in my last lectures, we have to take this values in under corona centimeter values. Because that is how it is given in the equation for power loss and the equation for critical disruptive voltage. And also visual critical voltage. So here this is substituted. The radius is 1.5, distance between them is 2 meter means 200. Next, what is this F? F is the standard frequency 50, F plus 25 by delta. What is the delta? Air density factor. We know that air density factor, okay, standard value is 1 generally, but that is under standard temperature, room temperature, and standard pressure. Okay, but in the given problem, they have clearly given particular temperature which is 40 degrees Celsius. Okay, 40 degree Celsius, and the pressure is 76 centimeter. So, using those temperature and pressure, calculate the air density factor delta. The equation for it is 3.92 B by 273 plus T. So, that's why it is calculated. So, pressure is 76, okay, 3.92 into 76, and the temperature is 40, right, 273 plus 40 degrees Celsius. So that is how calculating delta value, okay. So it is calculating delta, okay, and substituting here, okay, whatever calculated here, air density factor delta, and it is substituting here, and then this is constant 242.3. So in this, what is the only now unknown? So critical disruptive voltage Vc, which needs to be calculated. So we see here the critical disruptive voltage, its expression is m naught g naught delta r log base e d by r, okay, kilovolt per phase. So the equation for given for per phase, okay, and also its values in kilovolts. So now here everything, see the delta, again spacing between the conductors, radius of the conductor in centimeter, okay, substituting from the given data, and the radius of the conductor, okay, and G naught, its standard value. In the problem, it is not mentioned anything about the this G naught value. So potential gradient general value to 21.2 kilovolts. Okay, RMS value. Okay, RMS value we have to consider, because the voltages also all values are in RMS value. Now, and what about this delta? Delta just now we have calculated, that is also considered. Okay, the same value whatever we have obtained here, we substitute here delta, and what is that m naught is given in the problem, directly given, okay. So it's a 0.85, okay, m naught value given as 0.85. So consider here that value, so that value is 0.85, okay. So that is how all the values are substituting here for all the parameters, and calculating this Vc, okay. So so critical disruptive voltage first, that is how first calculating, and this value is okay, we are getting per phase value, okay, how much it is. So previous slide already given the answer, it is 125.9. So by you substituting all these values, we need to get the value as 125.9 kilovolts per phase. Now use this Vc to calculate power loss, coronal power loss. So here substituting Vc, per phase value 125.9, and voltage, system operating voltage 220 by root 3, right? System operating voltage, that is given 220 only, right? Yes, 220 only it is given. So that is the line value given. So we from that taking per phase value, so 220 by root 3 we substituting, and okay, so all values are okay known, so that's why substitute, and finally obtaining this P as, this is a, sorry, so this is a value, 0.0199 kilowatt per kilometer per phase. 0.01999 kilowatt per kilometer per phase. So by substituting like this, we are getting as 0.0199, okay, kilowatt per kilometer per phase. Okay, so that is how corona loss is calculated using the for the given problem. Okay, for the given problem. So now that clearly this is the equation for corona loss is per phase. Okay, corona loss per phase for with respect to one phase. Okay, per 1 kilometer. Okay, and in kilowatts. Next problem. A certain three-phase equilateral transmission line. A certain three-phase equilateral transmission line has a total corona loss of 53 kilowatt at 106 kV and a loss of 98 kilowatt at 110.9 kV. Okay, again three-phase line, equilateral transmission line. Okay, that means the three conductors are arranged. The distance between, if we take any two conductors, the distance is same. Now, it has a corona loss of 53 kilowatt at operating voltage of 106 kV and it has a corona loss of 98 kilowatt at 110.9 kilovolts. Okay, so different operating voltages it is given. Okay, different operating voltages and its corresponding corona loss. Its corresponding total corona loss. Okay. Now, of course, total means total corona loss for a three-phase line means we get the using equation P corona power loss, we get per phase corona loss. So, if you want total corona loss for a three-phase line, 3 into that value. Okay, multiply that value with using the equation whatever power loss we obtain, we multiply with 3. Okay, so that we will get the total corona loss for the three-phase line. Okay, of course, anyway, that is not the important factor here. Okay, look at the given problem. They have given different operating voltages. Okay, 106 and 110.9 and its corresponding corona loss. Okay, at 106 kV, the corona loss is 53 kilowatt and at 110.9 operating voltage, the corona loss is 98 kilowatt. Now, question is, what is a disruptive voltage? What is a disruptive critical voltage? That is a problem. Okay, so that is the first part. Then they ask, what is a corona loss at 113 kV? That is the next question. Okay. Anyway, first using the given first data, first calculate this VC. Okay, so they ask you to calculate VC, right? So what is the VC value? Now here, see that the answers. These are the answers we see on the slide. So okay, this much VC we need to get. So now, using given data, how to calculate? They have given different operating voltages and its corresponding power loss. Okay, so for that, consider the how to solve this. Consider the corona power loss equation. 242.2 into F plus 25 by delta square root R by D into V minus VC whole square into 10 power minus 5 kilowatt per phase per kilometer per phase. Now, because here they have not mentioned anything about the system operating frequency or air density factor, that means different temperatures, different pressures. They didn't mention anything. So, and they have given only about the power loss with its corresponding operating voltage. So from this equation we can say that okay, only okay, So only they have given power loss and they mentioned about the operating voltage. Okay, so we can say that the system frequency, the operating temperature and pressure conditions are same. Okay, that is the meaning. So we can say that as frequency and delta are same for both, okay, conditions, okay, for both cases under different operating voltages. Okay, so the above equation can be written as, it becomes power loss directly proportional to V minus Vc whole square. So that is a thing we can mention, we can consider. Okay, so because supply frequency about the temperature and pressures, okay, they didn't mention anything. Okay, so that means we can say that they are fixed, they are same. So from this equation, power equation, Corona power loss equation, we can consider power loss is directly proportional to only the factor V minus Vc whole square. The remaining parameters are taken as same, okay, for both cases. Now, so for first case, they have given the corona loss. What is the corona loss? First is given for operating voltage 106 kV. Corona loss is 53 kW. Okay, for first case. For first case, for first case, for first case, power loss is equal to, okay, what is that? 53. V is nothing but V is how much? 106. But remember, this is for phase value. We need to consider. Always given data is line value. So 106 by root 3. Say that equation 1. Okay. So 53 is a power loss. Okay. And what is the operating voltage? 106 kV, right? 106. Right. Okay. 106 by, that is a line voltage. So by root 3 gives per phase value. Next, minus Vc whole square. Next, for second case. For second case, what is the power loss and what is operating voltage? Power loss is 98 kilowatt and operating voltage 110.9. Sorry. 98 power loss and this is 110, right? Operating voltage. Operating voltage. Right, 110.9. Okay, so that is, okay, we can write 110 operating voltage, that is line value. So by root 3 gives a fair. So now divide equation 1 by 2 or 2 by 1. Dividing equation 2 by 1. Okay, what is that? It becomes 98 by 53. 110 by, okay, 110.9 by root 3 minus Vc whole square by 106 by root 3 minus Vc whole square. Okay, so it becomes 98 by 53 square root and this side 110.9 by root 3 minus Vc by, okay, using scientific calculator, okay, you can simplify this. Okay, so we can write it as equal to, right? So now what is the unknown here? Only Vc is the unknown, right? So we can calculate simple, very simple calculation. So this is how we can calculate Vc, critical disruptive voltage Vc value. Okay. So how much it is? Answer 54 kilovolts per phase. Okay, check using the calculator. We can calculate. Next. So that is the first part. Okay. asked to calculate critical disruptive voltage. Next, what else they ask? They ask what is the corona loss at 113 kV. They ask, okay, corona loss at another operating voltage 113 kV. Okay, so using the same phenomena. Okay, so like so far how we consider. So we are going to get power loss, this corona power loss at 113 kV, another voltage, operating voltage 113 kV. This is the answer. Okay. So same manner. So at 113 kV operating voltage. Okay. What is the power loss? V minus Vc, right? So they ask this is how much. Okay. So say that, okay, this is P R W. Okay, up to you. P R W we want to calculate. And what is this? V? 113 by root 3. And Vc is already calculated, 54, right? So say that equation 3. V is 113 by root 3. That is a point, that is a value of voltage where they ask, okay, to calculate the corona loss. So that V is 113 by root 3. Okay, and Vc value is 54 already calculated. So consider that. Say that equation 3. Now we want to calculate this corona loss. How can we calculate? Okay, using let's just to do equation 3 by 1, dividing equation 3 by 1. What we will get? Power loss, this corona power loss W or P, whatever. Okay, W by 53 equal to 113 by root 3 minus 54 whole square by 106 by root 3 minus 54 whole square. So this can be written as W square root of W by 53, 113 by root 3 minus 54 whole square, 106 by root 3 minus 54 whole square. So that is how, only what is unknown? Only W is a unknown. So which can be obtained as using this, okay, using our calculator. We can, okay, solve this and get the value is, this is the answer, 128. Okay, answer, that is finally the corona loss at 113 kV operating voltage. So this is how this problem is solved. Okay, this is how this problem is solved. So these are the references for these two explained problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.